Okay, so can you share, can you see my screen? Is it visible?
Yes, it's visible.
Right, amazing. Okay, so did you get time to go through, did you make any notes, by the way, in the last class?
No.
Okay, so is there any question, or did you go through things, did you have any question
I have
from
all of
the?
these things on my textbook, so I can
Yeah,
refer.
exactly. So that's what I meant. If you went through those, is there any question that you have from any of the topics that we have
No, not at the
covered?
moment. No.
Okay, it could be even apart from what the lecture that I gave, but in those in the range of those topics that we covered. If there is still any question that you
No, no,
yourself have,
no.
you can ask. Okay, amazing. So right, so we'll start from where we left off. I think one more class happened, but nobody was. I think. Did you take the class which happened on Thursday?
Thursday it was a demo class, I
Yeah.
guess. Yeah. I was the
You
only
were
one there.
right. Okay. Yeah. Okay.
Mm-hmm.
Perfect. So okay. So I think we ended at this point.
Yeah,
Did we
over
start
here.
scalars?
No, we didn't start scalars and vectors.
Okay. So all right. So we'll start scalars and vectors. I think I'll do all of these things again. Okay. So let's get rid of this. Right. So basically, a scalar quantity is any quantity which does not need a direction. Or you can say that you can specify a scalar, any quantity, you can specify it without mentioning directions, then that's called a scalar quantity. And a scalar quantity is just defined using numbers, right? So it's just, for example, you can say a mass of 10 kilograms, or you can even say time is, let's say, 10 seconds. You don't need to specify the direction for these things because the physics remains the same, whether you say mass is well, you don't really need direction for mass, right? You don't, it doesn't make any sense to say mass in what direction, right? However, then you have another thing, which is a vector. And in case of a vector, so let's consider an example. We'll start with an example. Again, I don't know if I gave this example before, but let's say you have a block and you want to push it. Suppose you say that I will push the block by applying 10 newtons of force. Now this is force, right? So this is force. Is this information enough to tell you what will happen to the block? So let's say you don't specify any direction, right? So you just say that I'm applying, you make a sentence, you say I'm pushing the block with 10 newtons of force. Now there are many possibilities. You could push the block from a particular side, and the dynamics of what happens will be different. So for example, if I push the block in this direction, then the block will move in this direction. It will accelerate in the direction of the force that I applied. If I push the block in this direction, if I applied the force from here, the block would have moved in this direction. So the direction will affect what happens after I apply the force, which means that to specify a force completely, I need the magnitude of the force, how much force I'm applying, and I also need to tell you in which direction am I applying this force. So any quantity that needs these two informations is called a vector. So is the idea clear between scalars and vectors?
I didn't quite get that. Can you give me like a clear definition of what magnitude is? Is
Oh, it's just
magnitude
a
the
number.
amount of
Yeah,
force
yeah.
applied?
So yeah, so it's the strength of the force. So how strongly am I pushing this mass or this block? How
Right.
strongly am I pushing it? So the higher the number, the higher the strength that I'm applying to this block. Right? So for example, so you can think in terms of mass as well, right? And that's kind of funny because the higher the mass, the fatter the person is, right? So it's just a number. So if the number is lower, then the quantity, you can say the amount is less. And if the number is high, then the amount or the quantity is more. So that's simply magnitude. Magnitude is just a name that you give to something like this. It's just a name. You don't have to get, well, actually in physics, we use names that are scary, but what they mean is very simple. So even vector, it's a kind of a scary name for a first timer, but it's really simple if you think about this example. So is the idea of magnitude clear?
Yes.
Okay. And did you understand what I was trying to explain with this block?
Yeah.
Okay.
I
So
think what you meant was wherever in the direction you apply the force, the object tends to move in the same direction. Is that what you meant?
yeah, that was the point, and I used that point to explain a vector. So if I push the block in this direction, if you can see the pointer on the screen.
Yes, I can see it.
This hand, yeah, okay, perfect. So if I apply the force in this direction, then the block moves in the same direction, right? So if I push it from this side, it will move in to that side. Now,
Right.
what if I pushed it from bottom? Then it would have moved to the top. So it doesn't matter. I could have pushed it with the same Newton force, 10 newtons of force, but the direction which I used this time was this direction. So what happened was different. So the block moves this way is different from the block moves that way. That's obvious, right? So the magnitude remained the same, but the direction which I applied the force was different. Hence, what happened later on, when the block moved, it moved differently. Right? So so for any quantity, if that's what happens, then that's called a vector quantity.
Right.
Similarly, I can give you an example with a velocity. If you want to specify so for example, let's consider a car, and the car is moving. Now, you can say the car moves with a speed of, let's say, 10 meters per second. But this information, this velocity, this information at the moment is not enough to tell you what is happening with the car. Okay, fine, it's moving and its speed is basically 10 meters per second, but where is it going? So if you want to know where is the car going, then you need to specify a direction. You could say it's going to the east. Now that's a direction. Now using this thing is direction and this thing is this magnitude. Now these two things together, they make a vector. And that vector, in this case, it's called velocity vector, which tells you both about the speed, which is 10 meters per second, and the direction, which is east in this example. So is this clear?
Yes, very much clear.
Okay, perfect. So that's basically scalar and vector. For scalar, you don't need any direction. You just have to specify a number. So it doesn't make sense, for example, like I told you about the mass, 10 kilograms is enough. You don't need to tell 10 kilograms to the left, 10 kilograms to the right. That information does not matter, right? So that's mass as a scalar. So that's your scalar and vectors. And here are some of the examples for scalars and vectors. When we'll start working with these, you'll be more familiar with what their definitions and what they really mean. Okay, so let's move on to this thing. I think we'll do this again as well. 1 second. Okay, let's get rid of this. All right. Okay, so now what you can do with vectors is you can add vectors. So for example, consider this example, same example, you have a block and you push it. Let's say now you're pushing it in this direction. And for example, one person is pushing it in this direction and the other person also pushes it in the same direction. So it's something very heavy and you need two people to move this object, this heavy block. So one person applies some force. Let's call that F1. So this is the force that this person one is applying. And then you have F2, which, sorry, are you saying something?
No, I didn't say anything. It's probably from your side.
All right, right. So yeah, we have, okay. So 1 second. All right, so yeah, we have two people and they're pushing this object. The force that this person applies is F1, and then there's some other force which this person applies. Let's call it F2. So these are two different forces. Now the block would feel the sum of these two forces, right? So the force that the block is feeling is F1 plus F2. So it's both of these forces together. So that's clear, right? So there's no question in that, or is there?
No, that's clear.
Yeah, so if two people are pushing the block, so the total amount of force that the block gets is the sum of both of those forces. Okay, perfect. So now we want to see how can we add these two forces. Well, one way it's very easy, right? You can just say the numbers of these forces. So if this applied 10 Newton, then this applied, if this also applied 10 Newton, then it would be simply 10 plus 10, which is 20 Newtons. But for example, that's not the case. For example, let's say you don't just need what happened, 1 second. You don't just need the magnitude, you also need the direction, the total direction. Well, in this example, this was pretty simple. Both the forces were exactly to the right, so the block would definitely move exactly to the right. But for example, let's say that you have a force like this. Let's see, you have a force which is 4 Newtons and it's applied at this point P. So at this point P, you have two forces which are being applied. So this thing, it looks a bit weird, but it's something like where you have this point P, let's say that this is a ball and it's point P, and the force, someone applies a force to it from this direction, and then the other person applies a force to this ball from this direction. Now this F equals 4 Newtons, and this is F equals 20 Newtons. Now, the thing with vectors is, as long as I don't change the length of this vector, and I don't change the arrow where this vector is pointing, I can simply move them around like this. Wait, yeah. So what I can do is I can pick this and I can take it over here. So all I did is I just picked this vector, right? I just picked this vector and I moved it from there to here. That did not change the arrow, right? It's still pointing in this direction. And I did not change the length of the vector as well. So the length of the vector basically corresponds to the strength or the magnitude of this vector, which is 4 Newtons. And the arrow where the vector is pointing, that is for the direction for the vector. So as long as I don't change those two things, I can do whatever I want with this vector. I can move it around. I can, well, the only thing I can think of right now is move it around. So what I can do is I move this vector over here, and now this thing looks like this diagram that you see over here, right? So now this thing, and now what I can also do is I can move this vector, this whole thing. I can, let's say I'll keep it at this point, at the center of this ball, right? So let's keep it over here. So again, I'm just moving them around. I'm not changing the direction. I'm not changing the arrows. I'm not changing the lengths of the vector. The only thing that I'm doing is I'm moving them here and there. So that does not change the vector. And if it does not change the vector, we use a word called invariant. So the vector is invariant, which, let me just write it down, invariant, which just means that the vector is not varying, And if something is not varying, it just means it's not changing, right? So the vector does not change if I move it around. So is this concept what I was trying to get across, the point of what we can do with vectors and where we can move them around, basically? Is that clear?
Yes, sir.
Right. So is everyone else also following along? You can unmute yourself and let me know. Or if you don't want to unmute, you can just type in chat box and just let me know if you're following along. The only problem with the chat box thing is I'll have to keep going into this Zoom thing and then check. So yeah, so I think someone has said something in chat. Yes, sir, I'm following. Yeah, so so the problem with this chat box thing is I'll have to keep going into this thing like this chat box and then see your messages because I don't get the notification for some reason. So it's better you can unmute yourself and just let me know if you have any problem, any question that you have, feel free to ask me, right? You can stop me anywhere and you can ask your questions. Okay, so now what we want to do with this thing is we want to add these two vectors together. So how do we do that? Well, basically, there are different ways of doing it. One of the ways is called a trigonometric method, right? It's an approach that we borrow from mathematics, and it's called a trigonometric method, where we use the Pythagorean theorem, the Pythagoras theorem, and we apply that to our triangle, which you'll see. We'll make a triangle out of this. How do we make that triangle? Well, these resultant of these vectors, just imagine someone pushing the ball in this direction and someone pushing the ball in this direction as well. What do you expect would happen to the ball? In which direction should it move? You can imagine in your head this situation. Someone is pushing something from it to the right and the other person pushes it to the upwards direction. Where should the ball move? Any idea, any clue, any guess?
In the air. On the air.
Yeah, by that, where do you mean it? Are you saying it would move in between these two directions?
Probably upwards because the force applied is more.
Yeah, so that's you're getting somewhere, but it would move like this. It would move in a diagonal, but this diagonal would be more to this side. So someone also said it would move in the air. Maybe I think that's what they meant, that it would move in this direction. So yeah, so this vector would be pointing more towards this direction, right? Because, and the reason for that is, you got it right, that there is more force in this direction. So it would be in the favor of this direction, upwards direction. But because there is also a force over here, it would also move slightly to this right side, right? So it would move slightly to the right as well. You can think about it. So picture a situation, or if you have something in your, you can just, if you have a book right now with you, just put that book on the table apply a force to that book. Let me just give you an example. So here you have a book. Take a book, do an experiment. Physics is all about experiments, right? So you do when.
Sir,
Yeah, sorry.
yes, on the left diagram, the
Yeah,
yes, the force is the force of 4 Newton is going upwards, and the force of 20 Newton is going downward, is going to the left.
right.
Right,
To
right.
the right. Yeah.
So can we change the forces? Because here it's going to the upward and here it's going to the left. The more 20 Newton
Oh,
force is going.
Yeah. So that was a mistake on my part. Let's just call this 4 and let's just call this 20, right? So I got what you're saying. Yeah. So this is equal to 20 Newton, and this was the point P. Okay, so yeah. And maybe that might have caused some confusion as well. So yeah, so that was the diagram. Okay, so yeah. So coming back to something that I was saying, just do an experiment. This is a book, right? I'm not very good with drawing, so let's just say that this is a book. Okay, and now what you do is apply some, put it on a flat surface, put it on a table, and then push it with one hand in this direction, and then push it with one hand in this direction. Do that at the same time. You'll see that the book tends to move like this, right? So it will move to the right as well, and it will move in the upwards direction as well. So whenever you're doing a problem in physics, try to imagine the situation in practical life, right? And so then when you do that, things will start making more sense as well. So now, so in this case, you see that the force that is more is in this direction, and the force that is less is in this direction. So you would expect this point P to move something like this, right? So it would be, this vector would point more in the direction where the force is more, right?
Yes.
Okay, perfect. So, but now this is not exactly how it would look like. It would, for the purpose of drawing, we'll just draw it like this, right? We'll just draw it like this. And this basically makes a triangle, right? A triangle, which is a right angle triangle. And now this length in terms of, now we are talking about length in terms of forces. So are you familiar with this theorem where you say this is the hypotenuse? This is, I think, if you have an angle over here, then this is adjacent side and this is the opposite side. And then you say that the hypotenuse squared is equal to the squared of adjacent plus the square of opposite.
Yes.
Yes. Okay. So everyone, is this okay for everyone?
Yes.
Okay, right. Okay, perfect. So what I can do from this point is let's call this new vector. You can give it any name. For our purposes, let's just call it R, which means resultant, right? So it's a resultant force. It's called resultant because it's a result of these two forces, 4 Newtons and 20 Newtons. It's a result of the sum of these two forces on this point P. So yeah. So now how you can find this R is simply, if you take, it's your hypotenuse. So I can just say it's R squared, right? Because hypotenuse is R. And adjacent, this base, or sometimes it's also called base, which is 20 Newtons, right? So in this, I'll put 20 and then this square, then plus, this is the opposite side. And remember, I can take this vector, right? This vector, let me just, because I cannot copy paste that diagram, so I'll just draw a vector on itself, and then I'll take this. So what I can do is I can take this vector and I can move it around, because I told you that would not change the vector itself, right? So I just moved it around from here, and now nothing is over here, but this vector moved over here, and I can do that, and this is now 4 newtons. So opposite side is now 4 and then squared. So what I did to write down this expression, is that clear for everyone in the meeting? Is this clear how we got 20 squared plus 4 squared
Yes,
as
sir.
r? Sorry, can you repeat?
Yes.
Right. So now it's simple mathematics. You'll just do this algebra and you'll get 416, and this is r squared, right? So this is r squared. Now if you want to find r, I think I'll do it over here. To find r, you'll just take the square root of 416, which is 20.4 newtons approximately, right? Okay, so that's the resultant force. So what does this mean? Think about it now. This means that, for example, if you consider this example of a book, and if I applied these forces to the book in this way, then the book would feel the total force as 20.4 newtons in this direction. So we'll work out the direction right now. We got the magnitude of the force, right? So this is the strength of the force with which the book moves, right? But now in which direction does it move exactly? We can compute that by using an expression which is tangent theta is equal to, okay, so we'll get into the proper derivation of this expression. From where do we get this tangent theta is equal to, should I do it right now? I think we'll do it when we encounter I think this is on the, this part is focused for forces mainly. So maybe should I do it, or should I leave it for resolution of vectors? Okay, let's do it. Let's derive from where do we get this other expression for angle. What I'll need to do is I'll just add another, or I won't have to add, I'll have space over here. So, okay, so basically it's something like this, right? You have this thing and you have this thing. So it's basically a triangle, and you have these are your angles, right? Now, this is the base. So let's call this direction X, this one, right? This direction is X, and this direction is Y. Now, this is your right angle. Now, let's say that this was your force F, right? So you can break down this force into its components as well. So what we just did previously in this part, we found the sum of these components as this R, right? Now, what I'm going to do is the reverse of what I just did over here. And that is, I'm going to have this R, look, and I'm calling it F, and then I'm going to break it down into its individual components like this. So we'll see how do we do that. So suppose that you're applying a force in some direction, right? And you want to see how much of this force is entirely in this X direction. And you want to see how much of this force is entirely in this Y direction, right? Because again, if you have a force that is a bit slant, and these are your X axis and this is your Y axis, then there should be some part of this force which is contributing
Sir,
entirely.
your voice is cutting out.
So is that happening for everyone? So then it might be a problem on my end. or is it?
That sounds clear to
Yeah.
me.
Okay, so it might be a problem at your end, maybe your internet connection. So I think you should check that. Can you tell me how much time is left in the meeting before it all abruptly ends?
It's 7:06. I'm not sure how much time is left.
Okay,
Probably 10
Uh,
minutes.
right. So actually, I got this notification a couple of minutes ago for 10 minutes. Okay, anyways, are you getting what I'm doing over here? Did you get the point where I can break this f into its different components, which are x and y?
Yes, I did get that.
Right. So that's what we will do now. So the
Hello?
x part. Hello, you can hear me? Are you saying something?
Sir, I think it was my internet problem.
Yeah. Okay. So you can hear me right now. You can hear me clear now. I think there is still some internet problem. Okay, so yeah, so what I'm doing is I'm trying to break this f down into its x direction and y direction. So the x part, using trigonometry, I can write this as cos theta is equal to f, right? And over this part, right, this side, which is, let's say that this is fx, the force in the x direction, this one, right? So this is you know those, I don't know how you memorized them, but there are these things, right? Sine is equal to opposite by hypotenuse. Are you familiar with these expressions?
Yeah, I've learned it as some people have curly brown hair that
Yeah, exactly.
they'll paint it black,
Exactly.
brown. I
Yeah,
don't know.
exactly. So that's one of the ways
Mhm.
to remember. Okay, perfect. So that I just used one of that rule to write this expression down. So cos theta is equal to this, which is hypotenuse, and base, which is adjacent, or you can say base, which is fx. So this is the force which is in the x direction entirely. So which means that the x component of the force is simply f cos theta. And similarly, you can use another trigonometric expression, which is this one, sine, and you can write sine theta is equal to this side, right? So let's call it fy. This is the force in the y direction. So this side, which is fy over f, right? Which is this hypotenuse. So from this expression, you can write fy is equal to f multiplied by sine theta. So that's f sine theta. And this is how we get those expressions for when you're resolving your vectors. When you resolve a vector and you say one component is f cos theta and the other one is f sine theta. So that's where you get these from. And now to get the expression for the angle, all you have to do is divide this expression, the sine one, with this expression. So let's do that. Fy is equal to f sine theta divided by this one. So for this part, I'll have divided by fx. And after the equal sign, I have f cos theta. So after the equal sign, I'll divide this by f cos theta. So this cancels, ff goes away. We are left with sine over cos, which is tan theta. You agree with that, right?
Can't we just use a simpler method?
Right.
Like,
Oh,
can't we just use
the-
the tan instead? The inverse one.
we will use the tan, the expression for tan, exactly. So we did not need to go through any of this. The only reason I'm
Mhm.
telling you all of this is so that you don't ask me where did I get this expression, which I'll just write down, which is tan theta is equal to the y component divided by the x component. So